Hi everyone, my name's Andrew and I'm a tutor for ENSC 3001 and we're making this rotational kinematics video because we found that a lot of students were having trouble making the link between what was presented in the content and then how to apply that to actual questions. So the point of this video is to go a little bit more into how to use the equations to figure out the questions. So what is rotational kinematics and when would you come across a rotational kinematics question and how would you recognize one? Rotational kinematics is whenever you have some sort of point of interest, we'll call it P, and you know about the motion of P in one reference frame. We'll call that the intermediate reference frame. So we'll just draw that here. So you might know the velocity of P, you might know the acceleration, displacement of P, all with respect to this one, the intermediate reference frame. And if you want to find out the velocity, acceleration of P in a different reference frame, so we'll call this the base reference frame, that's a Z. Then you would use this rotational kinematics concepts. Right? So an example, a really simple analogy might be you're driving in a car and a car drives past you at 30 kilometers an hour. Relative to you, you know that you're driving at 60 kilometers an hour and you're wondering, what does someone on the ground see that car driving as? And we know it's 90 kilometers an hour. But what you're actually doing is you're looking at the point of interest, which is the car. You yourself are the intermediate reference frame and you're finding out information about the car, or our point of interest, in terms of the base reference frame, which in this case is the ground. And one of the biggest problems students have is using these three equations. These are the three equations that you'll use the most in a rotational kinematics problem, and it does look a bit daunting. What do all these variables mean? What's R naught? What's little r? What's V rel? What's omega? So let's go through this, let's go through every single variable so that we can use these equations and we know how everything's defined. So we'll start with equation 1. This is an operator which is used to find the time derivative of any vector. So for example, you want to find the time derivative, so say your point of interest is spinning around at a certain angular velocity omega, and you want to find d omega by dt, so the angular acceleration. You would put omega here and omega here. So this first term, this is the time derivative of omega with respect to the intermediate reference frame. So imagine you're the intermediate reference frame. The time derivative of your point of interest, the time derivative of the angular velocity of your point of interest is this term here. Little omega, that's the angular velocity of the intermediate reference frame with respect to the base reference frame. So we'll draw that here. So if your intermediate reference frame is spinning with respect to the base reference frame, the angular velocity with which it's spinning is little omega. And so all the other little omegas, they're the same thing. Cool, so that's that. So we know everything in the first equation, we should be able to use it. The second equation is an equation for V, which is the translational velocity of our point of interest. The first term is dr naught by dt. What's r naught? R naught is defined to be the vector from the base origin to the intermediate reference frame origin. So dr naught by dt is just the rate at which that's changing. Or I guess the velocity of the intermediate reference frame with respect to the base reference frame. VREL. VREL is the velocity of point P with respect to the intermediate reference frame. So we'll draw that. So remember, it's with respect to the intermediate reference frame. Little omega we've discussed. What's little r? Little r is the position of our point of interest with respect to the intermediate reference frame. So this is little r here. And at this stage, we should know how to use the second equation because we know all of the variables, we know how they're defined. On to the third equation. The third equation is an equation for the translational acceleration of our point of interest. So we know r naught, so d squared r naught by dt squared is just the acceleration of the intermediate reference frame with respect to the base reference frame. AREL is the acceleration of our point of interest with respect to our intermediate reference frame. We've discussed these variables, omega dot. Omega dot is the rate at which the intermediate reference frame is changing its angular velocity. So it might be spinning and it might be spinning faster and faster and faster with respect to the base reference frame. So the angular acceleration is omega dot. And then everything else we've discussed. So at this point, we've defined all the variables in these three equations. Something to note, however, is that wherever you see rel, that means relative to the intermediate reference frame. So we also said r was the position of point P with respect to the intermediate reference frame. So we can write rel here, wherever we see little r, just so we know that anything that says rel beneath it means relative to the intermediate reference frame. Alright, so let's try and use these equations in an example. So our example is we've got an ant on a turntable. The turntable spinning around at a certain angular velocity and angular acceleration. And relative to the turntable itself, it's walking at 2 centimeters per second to the left. That's relative to the turntable. So we want to find out two things. Its velocity with respect to the ground and its acceleration with respect to the ground. So its velocity with respect to the turntable, we know it's 2 centimeters per second. And we want to find out how does an observer from the ground see its velocity. Now we're trying to find velocity, so it makes sense to just use our second equation, the velocity equation. So let's do that. Our v is going to be equal to, so I guess before we start that, we'll define our base reference frame and our intermediate reference frame. So our base reference frame is just going to be the ground. So x, y, and it's fixed. And we're going to make our intermediate reference frame the actual turntable. So at this point in time, let's just say little x, little y, and little z, which is coming out of the page, they're in line with our base reference frame. But what we're saying is that the intermediate reference frame is fixed to the turntable, so it's going to be spinning around as the turntable spins. But at this snapshot moment in time, let's just say they're aligned. Alright, so we'll use the second equation to find the velocity of the ant. So that's equal to, I'll just copy out the equation. Right. So this first term, that's just going to be equal to 0 because the origins of both of our reference frames are lining up and they're going to stay at the same point. So there's no change in the relative positions of our reference frames. VREL, so what's that again? It's the relative velocity of, it's the velocity of our point of interest, the ant, with respect to the intermediate reference frame. So we know that this is 2 centimeters per second to the left. So this is going to be negative, and we'll work in centimeters, negative 2I, where I is the vector for the x direction. So that's added to omega. So what's omega again? It's the angular velocity of the intermediate reference frame with respect to the base reference frame, and in this case, our intermediate reference frame is spinning around at 1 radian per second, right? So our omega, it's actually going to be in the z direction. What you do is you curl your right hand fingers in the direction it's spinning and your thumb points in the direction. So in this case our thumb's pointing in the z direction. So little omega is going to be 1 radian per second in the z direction, we'll call that K. And that's crossed with RL, which is this here. It's the position of our point of interest with respect to the intermediate reference frame. And so that's going to be 4I plus 3J. So now it's just a matter of actually doing the maths and doing the cross products, and we get negative 2I, and the cross product of these is 4J, take 3I, so we get negative 5I plus 4J centimeters per second, because we've been working in centimeters. So let's think about that. Does that make any sense? Well, the turntable is going to be spinning that way. The ant's already moving to the left. So it makes sense that the ant is moving in that direction. All right? So we'll raise that and we'll find the acceleration of the ant with respect to the ground. So now that we're finding acceleration, it makes sense that we want to use the acceleration equation, equation 3, and I'll just write that out. So again, we've already gone through all the variables. We should be able to identify everything. So let's start with the first term again. Remember, R0 is the vector between the two origins of each of the coordinate frames. And in this case, it's 0 and it's not changing. So this term is 0. What's AREL? It's the acceleration of the ant with respect to the intermediate reference frame. Remember, anything that says rel is with respect to the intermediate reference frame. So in this case, our ant's not accelerating with respect to the turntable, it's just walking at a constant 2 centimeters per second, so that's also 0. We've got plus 2 times omega, which was the angular velocity of the intermediate reference frame with respect to the base reference frame, and we figured out that was equal to 1k. From our example before, finding the velocity, we figured that out. And vrel, it's the velocity of the ant with respect to the intermediate reference frame turntable. So that's -2i. That's that bit plus. So omega dot, remember, is the angular acceleration of the intermediate reference frame with respect to the base. And in this case, because the turntable it's actually slowing down, its acceleration is into the page. So that's -1.5. Okay? Because we know that the z-axis is out of the page because x cross y is equal to z. And if it's slowing down, then it's actually accelerating at 1.5 radians per second squared into the page, which is in the negative z direction. That's why that's -1.5. So that's that. And that's crossed with RL. So the position of the ant with respect to the intermediate reference frame, and that's 4i plus 3j. And that's added to omega, we figured it was 1k, crossed with omega again, 1k, crossed with RL, which is just the same as this, 4i plus 3j. So now it's just a matter of doing the cross products. 1k crossed with -2i, that's -2j, times by -2 is -4j. And then the cross product of that and that is -6j. Take 4.5i. And then we have 1k crossed with the cross product of these, and that's going to be k cross I is 4j. Right. So these two make -10j, take 4.5i, and this cross product is 4i, k cross I, take 3j. So that gives us -8.5i, take 13j. So what our answer is telling us, and that's centimeters per second squared. So what our answer is telling us is that it's accelerating this way, so in the -i and the -j direction, which makes sense because it's on a turntable which is spinning, so it's expected to go undergo some sort of centripetal acceleration towards the center. Alright, so hopefully from this example you've gained a bit of an understanding on how to apply these three equations to a rotational kinematics problem and identify all the variables within the equations so that when you do a question, you know what to look out for and you know what to substitute into the questions. Thanks for watching.